Okay, so last time we were looking at started looking at the iterative algorithms and how to use those formulas that we saw to get the asymptotic time complexity. So let us continue on this. Okay, so this problem is called the element uniqueness problem. So the problem given here is you have an array of elements and you want to decide whether the array has unique elements or not. So what I mean by unique elements is no element should appear more than once. So if even one element appears more than once, the array is said to be not unique. Okay, so we want to design an algorithm for this purpose. So let us take up this array here, for example, and as you can visually see, the array has unique elements, means no element appears more than once. So how to determine it? So this is a brute force approach, the sense that we basically pick every element in the array and check if that element occurs anywhere else in the array. Now we make use of the array indexing as well as the symmetricness property, in the sense that for every element you need to just compare it to its right. So for index 0, we'll check whether the value of the element at index 0 is anywhere starting from 1 more than that index, which is 1 to the last index. Similarly, for index 1, we'll check if that element at index 1 is anywhere to its right. Okay, so we don't need to check if for example you pick, say, the element at index 2, which is 9. We need to check only whether 9 is anywhere to its right, because if 9 was anywhere to its left, we would have already captured that scenario when we checked for anything less than that index. So if 9 was, say, at index 0 as well as at index 2, when 9 was at index 0, we checked whether 9 is somewhere else to the right of index 0, and you would have found 9 to be at index 2. So that's why we make use of that, what I call this the symmetric property. So if you see the pseudocode for this, for I equals 0 to n minus 2, we run the j loop from I plus 1 to n minus 1. So if you think about this as I is index 0, the j loop will run from 1 to, in this example, 6, which is n minus 1. So 0 plus 1 to n minus 1. Then if I is, say, 1, the j loop will run from I plus 1, which is 2 to n minus 1. So that's why we have j always starting from I plus 1, starting from the right next index. Now if you see the last index for I, we go only up to index I equals n minus 2, because we have to check to its right. So the last valid index is n minus 1. This is indexing starting from 0. So we go from 0 to n minus 1. So the last index is I equals 0, n minus 2. We check j equals I plus 1 to n minus 1. So j will be n minus 1 to begin with. Now if any of those I and j values, so for example, if I found my phi to be here, then if when I start with I equals 0, I check phi is anywhere to its right, I find my phi to be at, say, this index j, which is 3, I can stop right there and say the array is not unique. I don't have to really do all the comparisons. So that's why as we analyze the time complexity, we have to think about what is the best case and worst case and all those stuff. Okay, so let us do that. So at the best case, the scenario would be something like this. We have the first two elements as the same element, then we start from index I equals 0, j equals I plus 1, a of I equals a of j. So right there we can stop and return false, telling that the array is not unique. If the elements are different elements, that is when we have to really do all the pairwise comparison. We compare 5 with 8, they are not the same, so move on. 5 with 9, not the same, so continue. 5 with 7 and so on. Now in the first iteration, that is for I equals 0, for that loop we checked whether 5 is anywhere to its right, but that's not sufficient. You have to check for every other element. So then that's why we run two loops. One is for the I loop that will pick an element at index I and run the j loop from I plus 1 to n minus 1, and then move on the I value to the next index, which is 1, and then run the j loop from I plus 1 to n minus 1. Okay, so in the case here we pick j I equals 1 now, then check if 8 is anywhere to its right. If not, like in this case, continue. Then I is 2, check if 9 is anywhere to its right, and move on. So the last comparison we will be doing is I is n minus 2, j will be n minus 1, check, compare 3 and 2. They are not the same. So once you have made all the pairwise comparisons and still we have not returned false, means you're still in the program, then we can come out of the for loop, the I loop, and say return true, means the array is unique. So the basic operation here is the comparison operation, checking the element at index I or comparing its value with the element at index j. If they are the same, we can stop and say the array is unique, not unique, otherwise we continue the comparisons. So as I said, the best case is just doing one comparison. If the first two elements are the same, we can say the array is not unique and stop the program. The worst case is if the array is indeed unique, we have to do all the pairwise comparisons and then decide the array is unique. The worst case would also happen if you have an array of something like this. The only last two elements are the same. So in order to find out such a thing, you have to do all the pairwise comparisons and then only decide the array is not unique. So we have worst case for two scenarios. So either way we have to do the maximum number of comparisons. So the best case is one comparison if the first two elements are the same. So now what we have to find out is what is the worst case number of comparisons. So for that we'll use a summation formula. So in order to find out what is the summation, look at this pseudo code or the logic. We run the I loop from 0 to n minus 2 and the j loop from I plus 1 to n minus 1. So for now a particular combination of I and j, we do this comparison, and how many times we do the comparison for a particular j, for the particular jth iteration, which is run as basis of the ith iteration. We just do one comparison. So that's why we write the summation like this. For I equals 0 to n minus 2, which is the range for the index of the outer loop, and then the j loop will run from I plus 1 to n minus 1, and that's the summation, j equals I plus 1 to n minus 1. And within the inner summation we write 1 because we do just one comparison within the inner loop. So this is how, given a pseudocode, a for loop or a nested for loop like this, we come up with the summation. For I equals 0 to n minus 2, sigma I equals 0 to n minus 2. For j equals I plus 1 to n minus 1, sigma j equals I plus 1 to n minus 1, and we do one basic operation. So that's why we do 1. If you do the basic operation 2 times or 3 times, the corresponding number should be put here, 2 or 3, whatever the number is. Now, so the rest is how to solve this summation. Now, in order to solve the summation, we have to apply one of the formulas that we have seen earlier. Now, the formula that fits with what we have is having a constant, or in this case 1, inside the summation. So you have lower limit to upper limit 1 is upper limit minus lower limit plus 1. So let us apply this formula and see what happens. So that's for the inner summation. So you don't do anything with outer summation yet. we're trying to solve the inner summation for j equals I plus 1 to n minus 1, 1. So the formula is, so again keep the outer summation as it is. For the inner summation is upper limit n minus 1 minus lower limit, which is I plus 1 plus 1. So now let us try to simplify this summation, this expression. Let me see if there's any questions. Okay. So you have n minus 1 minus, so I'm taking the minus inside, so it's minus I minus 1 plus 1. So now this negative 1 and 1 can cancel off. So it's n minus 1 minus I inside the summation. So now outer summation goes from I equals 0 to n minus 2. So now we have to solve this summation. Now there are different ways we can solve this. One way that we typically do use is this, when you have scenario like this, open up the summation in the sense that substitute different values of I and expand the summation and write it down. So this is, and the summation is from I equals 0. So when I equals 0, it is n minus 1 minus 0, which is n minus 1. Then I equals 1, it is going to be n minus 1 minus 1, which is n minus 1 minus 1 is n minus 2. And keep going like this until I equals n minus 2. It's going to be n minus 1 minus n minus 2. So once we have written like this, simplify this. So it's n minus 1 plus n minus 2 plus the last term is n minus 1 minus n plus 2. And that's going to be n minus 1, sorry, so it's going to be n minus 1 minus n. So the n and n will cancel, minus 1 plus 2. So it's simply going to be 1. So basically we have summation like this. So n minus 1 plus n minus 2 up to 1. Look at it in the reverse order because summation is again symmetric. So it's 1 plus 2 up to n minus 1. So last time we saw a formula where sigma I equals 1 to n. So I said sigma I equals 1 to n means n times n plus 1 over 2. Whereas here we have 1 plus 2 plus up to n minus 1. So if we have 1 plus 2 plus up to n, it is n times n plus 1 over 2. So now put n equals n minus 1. Then we are going to have n minus 1 for capital N, then n minus 1 plus 1 over 2, which is simply n minus 1 times n over 2. And that's what I have put here. So n minus 1 times n over 2 is approximately n square over 2, in the sense that if you expand even this, it's going to be n square minus n over 2. And n square over 2 is the most dominating term. We can discard the lower order terms. So the best case is 1 comparison and the worst case is n square over 2 comparisons. So what goes inside the asymptotic notation is the worst case, because here the best case is different from most case. So we use a big O notation, and you can say n square over 2, but again we discard all the coefficient and the lower order terms and we just simply say n square. So that is the asymptotic time complexity of this algorithm for finding for checking whether an array of elements is unique or not. Okay, any questions? Okay, so let me save this video.